of a series of 3 or 4 lectures on Bayes networks or graphical models. Graphical models are a representation for probability distributions that turns out to be very convenient, especially for thinking about many of the kinds of learning tasks that we're considering. So it turns out that this is actually a very popular basis for many machine learning algorithms. And in fact, if you read the proceedings of the International Conference on Machine Learning or of the NIPS conference, Neural Information Processing Systems, which are probably the 2 dominant machine learning conferences, annual conferences these days, then you'll see that probably more than half of the papers, the research papers in these conferences, use graphical models as the basis for the work that they're doing. So it's a very important part of the field of machine learning. And hopefully you'll appreciate why by the end of today's lecture. But the key idea is this. It actually derives from what we've already discussed when we talked about naive Bayes. And remember, we motivated the idea of using naive Bayes because, number one, we wanted to use some kind of probabilistic basis for our learning system. But unfortunately, number two, we realized that if we tried to represent the entire joint distribution among a large collection of variables, for example, even just n Boolean variables, we'd need some number of parameters that was exponential in n just to write down the joint distribution. And so that bothered us, and we decided we would use the conditional independence assumption of naive Bayes in order to defeat that complexity. And then we found, well, if we used naive Bayes and made that conditional independence assumption that all the x sub i's are conditionally independent, given the y, then we could get away with, in the case of naive Bayes, a linear number of parameters in n instead of an exponential number in n. Okay, now, some people complained, and I think with good reason, when we brought that idea up, that this naive Bayes assumption is really dramatically incorrect in many, many domains that we use it in. For example, you now have some experience applying it to document classification, where you make the truly ridiculous assumption that the words in the document are conditionally independent of one another given the category of the document. That assumption really is false. You could test it statistically and see for yourself. But still, we like naive Bayes because, well, you have to do something to be tractable. Here's the motivation for graphical models. It turns out graphical models are a way of positioning ourselves midway along the 2 points of the spectrum that we've discussed. So we discussed the possibility that we'd represent the full joint distribution over n variables with no assumptions, and we realized that was intractable. And so then we leapt to what I consider the other end of the spectrum, where we said, okay, let's just assume that every single x sub I is conditionally independent of all the other x sub j's given the target variable y, which is a truly dramatic set of many, many conditional independence assumptions. And so what graphical models do is they give us a chance to select out certain conditional independencies that we like and introduce other dependencies that we believe really do exist. And in that way, we can kind of navigate the spectrum from very tractable but ridiculously over-simplified model of naive Bayes to truly intractable, though, of course, very rich representation of a full joint distribution with no assumptions. And so graphical models are important primarily because they give us a way of writing down in advance and, in some cases, even learning what are some of the conditional independences and dependencies that we'd like to assert among the variables, and then designing learning algorithms around filling in the needed parameter estimates to give us our probability estimates, either the joint distribution or, of course, if we have that, P of y given the vector of x's. So that's the idea of graphical models. It gives us a way of writing down essentially conditional independence assumptions. And there are really two broad classes of graphical models that are used in the field. We're going to focus mostly in this class on directed graphical models, which are often called Bayesian networks, although Bayesians bristle at that because many of the learning algorithms for Bayesian networks are actually frequentist methods, not Bayesian methods. But it's okay. We'll put up with the bristle. There's another class of graphical models that are undirected. The edges aren't directed. And we won't really, in this class, spend a lot of time. But if you're interested in this area, the machine learning department offers a complete semester-long course on graphical models. And once you've had this class, you've got the prerequisites you need to take that class. So you're welcome, if you're interested in this area, to follow up that way. So let's proceed with just to remind us all, conditional independence, of course, is the assumption we talked about when we talked about naive Bayes. Just to remind you, when we say that random variable x is conditionally independent of random variable y given random variable z, we mean exactly this. We mean that the conditional distribution of x given y and z really doesn't depend on y if we have z. And we gave an example previously. Now there's another notion of independence which is a little different that people often talk about, which we'll call marginal independence. And basically it's a simpler notion in some ways. It just says the joint distribution over two random variables, x and y, or let me put it this way, two random variables, x and y, are defined to be marginally independent if their joint distribution can be written as the product of their individual marginal distributions. Okay, and again, terminology-wise, we call these things marginals, and in contrast to the joint distribution. Okay, so this is just kind of to swap us all in on conditional and marginal independence. Now, here's a typical Bayes net, where in this case I have all those blue boxes represent random variables. And I might have a problem where I have data about each of those kind of random variables. And I might be interested in learning the joint distribution over those, or maybe learning to predict the X-ray result of somebody based on whether they've been in Asia lately and whether they are a smoker. And so here's a typical Bayes net. And informally, we'll get formal here in just 1 minute, but informally what this Bayes net represents is the idea that there are a bunch of independencies, conditional independencies among this collection of variables, and the edges here really are kind of description of the dependencies among the variables. So for example, the outcome of whether you have lung cancer might, for example, depend on whether you're a smoker, but not so much on whether you visited Asia. So the arrows informally represent kinds of dependencies. And in fact, it turns out we'll be able to attach a formal semantics to these kinds of graphical models that allow us to say that this graph, and writing this graph this way, corresponds to saying that the joint distribution over all those variables can be factored out, can be written as the product of the following conditional distributions. And again, we'll see exactly what the rules of the game are, but I just want to give you a quick impression. So when we have a graphical model, the edges and the form, the structure of that graph imply a particular form for the joint distribution over all the nodes. X1 through X8 here are the same 8 nodes in our graph. So in a graphical model, each node in the graph corresponds to some random variable. And the graph as a whole tells us how we can represent the joint distribution over all the random variables represented by the graph nodes, how we can represent that joint distribution as the product of a number of simpler distributions. And if you think back again to naive Bayes, that's basically what it gave us, right? It let us write the probability of x1, x2, x3, and x4 given y as the product of these other simpler terms, the probability of x1 given y times the probability of x2 given y. But now you can see here from the form of these distributions that they can be more complex. They don't have to be simple, one variable conditioned on one other variable. They can be more complex kind of terms. But the joint distribution, according to the rules of the graphical model, allow us to factor this joint distribution in terms of this product. And then the argument for doing that is very similar to our argument for using naive Bayes. It allows us to reduce the number of parameters that we need to use to represent the joint distribution, and it allows to improve the tractability of reasoning about, of answering probabilistic inference questions, and improve also the tractability of learning the joint distribution because of these assumptions. Okay, so let's look at, in more detail, one of my favorite graphical models. This one I devised myself as a model of when I decide to windsurf. So you'll see that there are 5 random variables in this graphical model, and that they're interrelated by this graph. And let's use this to look into how a graphical model represents a specific probability distribution. So it's written right here. First of all, these kind of graphical models that have directed edges, as I mentioned, we'll call these Bayes networks. And a Bayes network is simply a directed acyclic graph. Okay, directed means the edges have arrows on them. Acyclic means there are no directed loops in the graph. So you'll notice that even though there's a kind of a loop here, if you follow the arrows, you can't loop. So there's, we might call an undirected loop in here, but there's no directed loop. So it's a directed acyclic graph where each node represents a random variable, as we said. And here's the other half of what we need to specify in order to have a fully defined probability distribution over our random variables. We associate a conditional probability distribution with each node in the graph. And furthermore, that conditional probability distribution, say for node n, gives us the conditional distribution of n given its immediate parents in the graph. And here's one example for the random variable windsurf. And if we go over here and look at windsurf, you can see it has 2 immediate parents in this graph. Lightning and rain are the 2 parents that have directed edges going to windsurf. And so what we need to do for the windsurf node is provide the specification of how windsurf, let's say each of these is a Boolean variable. So we need the probability distribution on windsurf being true or false, conditioned on the probabilities for the two random variables, lightning and rain. And here is such a conditional probability distribution. You can see the parents are lightning and rain. There are 4 possible configurations for those Boolean valued parents. They can both be true, both be false, etc. And for each of those, we need to specify the probability on windsurf. And so this table fully specifies the probability, the conditional probability of windsurf given its immediate parents. Okay, very simple, very straightforward. And by the way, we're going to get later to how we learn these graphs, but I think it's useful, and so we're dividing up our lecture sequence into, initially, let's just figure out what the representation of probability distributions in terms of graphical models is. And then once we get that under our belt and we understand it well, we're going to move on to, well, how would we learn these probability distributions? So for now, we're just looking, don't worry about how we learn these things. Let's just figure out what the rules of the game are and how a joint distribution is being expressed in terms of the graphical model. Okay, so there's the idea. It's actually very simple. And once you give me a graph like this, a directed acyclic graph, and you give me for each node in that graph the conditional distribution for that random variable conditioned only on its immediate parents in the graph, then you have given me everything I need to know to write down the joint distribution over all those random variables. And the rule for writing down that joint distribution is pleasantly simple. Oh no. I have a little font problem. Let's write it down. The joint distribution over all these variables is defined in terms of these conditional probability distributions. And in particular, if I have a collection of random variables, let's call them x1 through xn, then the joint distribution over those random variables, given a Bayes net like this, is simply the product over each node of its conditional probability, given its immediate parents. I'll use this notation to denote immediate okay. And so that's it. Basically, the rules of the Bayes net graphical model are, once you specify a graph with certain edges and you give the conditional distributions of each node conditioned on its immediate parents only, then you've specified everything you need to know the joint distribution over all those variables. It's just the product of all the conditional distributions. Okay. We'll go through several examples, but this is, I wanted to start with that definition. Yes?
So does that mean thunder is excluded as a possibility once you reach windsurf? You have to extend the graph in some different way if you reach that node?
This is not a graph that you're following to solve a problem. This is simply a graph that expresses in a different notation of joint distribution over a collection of variables. So the only questions we can answer from this are questions that pertain to the joint distribution over the variables. So we could ask questions like, what's the probability of windsurfing given that storm clouds is 1? We could ask that. Or And given that we don't know the values of the other variables, we could ask that. We could ask anything that we can ask once we know the joint distribution. And as we're going to see, by the end of today's lecture, you'll know how to answer those in principle, although there will be some tractability issues that remain if it's a big graph. Okay. Yes?
Why do we even have an edge connecting lightning and windsurfing?
Oh, why do I have lightning connecting to windsurfing?
Yeah,
Because I never windsurf when there's lightning.
right, so why would you even have an edge connected? They're unconnected.
We haven't gone through what the rules are for the conditional independencies. But informally, the edges mean that things do depend. So I have an edge from lightning to windsurf because whether or not I windsurf depends very strongly on whether or not there's lightning. Okay? Given that I know whether there's lightning, it doesn't depend as much. It doesn't depend on whether there's thunder. And in fact, that conditional independency is implicit in this graph, as we'll see in a sec. So let's ask, what can we say about the conditional independencies given a graph like this? And here's one easy to remember thing that we can say, although it's not the only thing, as we'll see on Thursday. But here's one easy to notice thing we can say. Whenever you have a directed base net, each node is conditionally independent of its non-descendants given its immediate parents. Okay, so let's pick a node here, like windsurf. So windsurf is conditionally independent of its non-descendants. That'll be like thunder. That's not a descendant in this graph. Conditionally independent of thunder given its immediate parents. So given lightning and rain, windsurf is conditionally independent of thunder, according to this rule.
So is storm clouds non-descendant of windsurf?
According to this rule, is storm clouds conditionally independent of windsurf given rain and lightning? Yes. Yes. Storm clouds is not a descendant in this directed graph of windsurf, right? And so given the immediate parents, lightning and rain, windsurf is independent of storm clouds. So according to this model, if there are storm clouds, but we know there's no lightning and we know there's no rain, then we can calculate the probability. I should put it another way. According to this graph, if we know whether there's lightning and whether there's rain, we can compute the probability of windsurf without looking for whether there are storm clouds. Mm-hmm.
It seems a little weird, though, because if thunder is dependent upon lightning and windsurf is dependent upon lightning, that given thunder, one could get...
Okay. Okay. All right. So this is a question about whether I should obey such a conditional independence assumption. I don't want to debate the philosophy of whether it's wise to windsurf without looking at whether there are storm clouds. So I'm not trying to defend this particular model as the truth. I'm just bringing this up as an example of how we can represent a Bayes net.
So I guess what my point is, in this case, if you see thunder, then thunder is dependent upon lightning, and windsurfing is also dependent upon lightning. So given thunder, it seems like that would influence windsurfing, even though they should be conditionally independent.
Okay. So the comment is, even according to this, it seems like windsurf should not be conditionally independent of thunder given lightning. That's your point? But that was actually just the example, as you recall, we used when we introduced the notion of conditional independence. We actually used the example that thunder is conditionally independent. Oh, no, we didn't use windsurfing. We said lightning is conditionally independent. No, sorry, we said thunder is conditionally independent of rain given that there's lightning. That was our example. So again, we could argue about whether I should draw more edges in this graph, but We can't argue about what the formal rules of the game are. They are exactly the only thing we need to do to define the joint distribution from a graph in the conditional probability tables is this definition. So here is the full definition of a Bayes network. It represents the joint distribution where each node is a random variable, the edges denote dependencies, there's a conditional probability distribution associated with each node, defining its distribution conditioned on its immediate parents, and then the definition is exactly that the joint distribution of those variables is defined to be the product of those conditional distributions. And then, as we'll see, we can derive a bunch of conditional independencies from these ground rules. And those conditional independencies will include, in fact, that would be a good homework question, but we're not going to ask it. From those rules, you should be able to prove that each node is conditionally independent of its non-descendants, given its immediate parents. Okay, so there's the definition. And now everything that we're going to do in this lecture and next two is obvious from this. Well, obvious is a bad word. Follows from this. So if you ever forget all the other stuff, just remember this. And if you have enough time and you think it through, you can derive everything else that we're going to say for the rest of this lecture and the next two. Because this is really the full definition of a Bayes net. As I said, a Bayes net is simply a way of having a graph and a collection of conditional distributions represent a joint probability distribution over a collection of random variables. That's it. And there are a lot of interesting consequences of setting it up this way. Yes?
What happens if the graph does become cyclic?
We don't allow we don't allow directed cyclic graphs. So there is a limit to the kinds of distributions you can represent.
Is there any case in which you would use the joint probability of all the parents of a node in order to get its probability? Or do you just treat all the parents separately?
I don't think I fully understand that question.
So when you're calculating the probability of xi, it's based on its conditional probability given each of its parents multiplied together, right?
Right.
Would you ever use its probability given the two or any number of parents jointly, or is that the same?
Oh, okay. So the question is, would you ever use the probability of some node and its parents together? And the answer is yes. We're going to combine these in many, many ways. In fact, already, if you think about what we said when we introduced joint distributions the first time, back in, I don't know, lecture 2 or 3, and we talked about joint distributions, and we built this huge table, you know, one row for every possible configuration of the random variable values. We'd get a different row. And then we wrote down the probability that each variable would take on this particular collection of values. We wrote down its probability, and so we had one row in the table for every configuration. Well, in a minute, we'll see that we can very easily calculate the joint probability of any given configuration of random variables, any given assignment of values to the random variables. We can easily calculate the joint distribution, or the probability of that joint assignment. And so, effectively, it's very easy to fill out that table from this graph. And then, as we said when we talked about joint distributions that first time, well, once you have the joint distribution, you can compute any conditional distribution, any marginal distribution that you want, just by taking subsets of the rows in that joint distribution. So already you can see kind of that's the default method for doing inference of any conditional or marginal distribution we're interested in among any subset of these variables is just the same as what we were doing with that joint distribution table. Okay, so let's go ahead, because I think a few examples will really help. And also, you notice I've been using, with prosodic emphasis, the term immediate parents. I just want to be upfront about the terminology I'm going to use. So, and this is standard in the field. So I'll say that the parents, and I'll write it PA of X, the parents of a node X, are just its immediate parents in the graph. When I want to talk about its immediate parents plus their parents, I'll use the term antecedents. And similarly, when I say children, I mean the immediate children. And when I want to talk about children plus grandchildren plus great-grandchildren, I'll use the term descendants. Okay, so mostly we'll be just talking about parents and non-descendants. Okay, so just to keep our terminology straight. Okay, so now let's see, how would we represent, well, we said how we'd represent in a Bayes net the joint distribution over a collection of variables. We said it will just be the product over every node of its conditional distribution. But let's think for a moment about how that relates to the chain rule. So the chain rule, of course, is just a general fact about probabilities that says if we have a joint distribution over a collection of random variables, then by the chain rule, we can always write that as just the product where we peel off one variable at a time. So this would, peel off the storm clouds variable, and then conditioned on that, we'll take the next variable L. Conditioned on those two, we could take the next one R. Conditioned on those three, take T, and so forth. That's just the standard chain rule. We don't have to make any conditional independence assumptions to use the chain rule. It's just a fact about joint distributions. So in other words, if we make no conditional independence assumptions, we don't even have to use graphical models, we can always factor the joint distribution over a collection of variables via the chain rule. And if we do it for these 5 variables, that will just turn into the joint distribution is the product of these 5 terms. Okay, and again, if you're having a little trouble thinking about what does it mean to multiply distributions together, just keep in mind that whenever we say these things, we always mean for all x and for all values that these could take on, the probability that they take on those particular values can be expanded out this way. Okay, but now for the Bayes net, we're saying something else. We're saying, well, the rules of the Bayes net allow us to represent that joint distribution as a different product. So what is the product? How would I write it out in this, for this windsurfing Bayes net that we just said? Well, let's start with, so now I would say, well, the joint distribution on all these random variables given that Bayes net, this says I can factor it into the product over every node of its probability conditioned on its immediate parents. So let's start with S. What are the, oh, S has no immediate parents. So that'll just be P of S. Okay, what about L? The immediate parent of L, there's just one, it's S. So that means we can do that. R is a similar thing. R has only one immediate parent, so we can do probability of R given S. T has only one immediate parent, so we can do the probability of T given L. And then W has, well, it has 2. So now we're going to have times the product of W given L and R. Interesting. So now, you see, all we did was apply our definition of the Bayes net and how how it means that we can factor the joint distribution in terms of subcomponent distributions. But if I line that up against the chain rule, which is making no assumptions at all, it's just going to be true of any joint distribution, you can see the difference is, well, we've got these same two terms, but whoa, now we're saying R given S doesn't depend on L. We're saying R is conditionally independent of L given S. And son of a gun, that matches the rule we said. A node is conditionally independent of its non-descendants given its immediate parent. So R is conditionally independent of L, that's a non-descendant of R, given its immediate parent S. And that's why we could write P of R, we could shrink down what the chain rule would have given us to just P of R given S instead of P of R given S and L. And similarly, we can shrink down this term and this one. So you see, I find it very useful to think about the chain rule whenever I think about a Bayes net, because you can see all it's doing is giving us the same number of terms. In the chain rule, we'll always have a number of terms which is equal to the number of variables in our joint distribution. And here we will always also. It's just that some of those conditionalities are removed. So it's a very nice way of thinking it. And now you see what I meant when I said in sentence 1 of the lecture, Bayes nets are a nice way of allowing us to make selective conditional independence assumptions. We don't have to make none. That's what the chain rule does. And we don't have to make them all. That's what naive Bayes does. We can just make all kinds of weird and wonderful combinations of them depending on what graph we draw to represent what independences we presume exist in our domain. Yes?
So is this equation you've written the way of saying the probability of seeing these 5 observations SLRTW?
Yeah, think of it this way. Underneath all these, what I really mean is for every little s, little l, little r, little t, and little w value that those random variables could take on, the probability that s takes on little value s and l takes on little value l and so forth is the probability that s takes on that same little value s and etc. So that's what I mean when I say whenever you kind of get confused about what does it mean to multiply these distributions, just keep in mind that we just mean universally quantified over all the possible values those random variables can take on. Okay, so now we're off. You see this is going to get to be pretty interesting. So now let's ask our standard question. If we have a joint distribution of 5 Boolean random variables, and I make no independence assumptions, so I want to represent the full joint distribution, how many parameters will I need to write down to represent the full joint distribution over 5 Boolean variables? So how many possible combinations of 1, 0 values are for these 5 variables? Well, there will be 2 to the 5th possible combinations, 2 to the 5th strings of length 5 with 1s and 0s in them. And I'll need a probability for every one of those except 1, because they have to sum to 1. So 2 to the 5th minus 1. Okay, and that's the same thing we said when we put down the joint distribution in table form. We had 2 to the 5th rows. We said, okay, we'll need to write down a value for the probability in each one of those rows except for 1. Okay, now what about this Bayes net? Well, let's start with windsurf. How many parameters do we need here? Taking into account that some of these things sum to 1. I think I need these 4. Right? Because windsurf is either true or false, so once I know the probability that it's true, I can just calculate 1 minus that as a probability that it's false. So I need 4 for this guy. How many do I need for rain to write down its conditional probability table? 2. I agree. Why? Because storm clouds could be 1 or 0. Suppose it's 1, then we have to worry about the probability of rain being 1, given that storm clouds is 1, and the probability that rain equals 0, given storm clouds equals 1, but they sum to 1. So we just need 1. But then, of course, storm clouds could also be its other values, so we need 1 for that, too. Okay, how many for lightning? 2. You don't even have to think. Picture is isometric, it's the same. For thunder? 2. It only has 1 parent. The fact that that parent points to something else is really irrelevant in terms of we still need 2 because we need the probability of thunder conditioned on lightning. Right? And we need the probability of lightning conditioned on storm clouds and so forth. Oh, what about storm clouds? 1. It has no parents, but we still need the probability of storm clouds being 1 and 0, so that'll cost us 1 parameter. Okay, so if I add that all up, I get 11. Anybody know what 2 to the 5th is? Okay, so we win. We have fewer parameters to estimate, and of course because of those conditional independence assumptions that are implicit in the way that we drew the directed acyclic graph. Okay, good. Just for fun, here's a slightly more elaborate Bayes net due to somebody other than me who was interested in modeling how you would diagnose your engine and whether the engine starts and the condition of the fuel pump and whether the starter is working and whether the radio works when you turn it on and so forth. So this is just to give a quick example of a more elaborate Bayes net to get us thinking about realistic problems. And here you can see there are a lot of conditional independence assumptions implicit in this graph, right? What would this graph look like if there were no conditional independence assumptions? Every node would be connected to every other node is one comment. What's that? You haven't said anything to me about the direction of those arrows. Yes? Would it be a decision tree? Not exactly. So think of it this way. Remember, we just said that the joint distribution makes no, the chain rule factorization of the joint distribution made no conditional independence assumption. That's just a fact about joint distributions in general. So, if we just wrote out the chain rule expansion of the joint distribution and then used its conditions to go back to what the graph would be, we should get the answer to our question, right? Let's see if that's my, no, I don't want to do, okay, no, I don't want to do. I'm going to zoom ahead because I have this question. There we are. So let's consider, suppose I just have 4 random variables. That'll make it small enough that I can actually write it down on this page. So I want to represent the joint distribution over 4 random variables, assuming no conditional independence assumptions. Every node would be connected to all of its antecedents, but the question is, what are its antecedents? So let's do it this way. I just want to say, let's apply the chain rule again. Chain rule. And the chain rule says we can write this as P of x1 times P of x2 given x1, right? Times P of x3 given what? x1 and x2 times p of x4 given what? Right. Okay. If we can write it out that way, then what's the implied graphical model? Well, here's x1 appears to have no parents at all. x2 appears to have one parent. Better make that a directed edge, right? x3 has two parents, two immediate parents. x4 is conditioned on three things. Non-planar graphs are just fine. They just have to be directed acyclic. Okay, so there it is. That's the Bayes-Net representation of a joint distribution over 4 random variables with no conditional independence assumptions. How do I know that? Because I just used the chain rule to factor the joint distribution. There are no conditional independence assumptions implied by the chain rule. And then, you know, I just inverted our rule for how you went from a graph to the factorization, and you can obviously see that given this graph, we would get exactly that factorization of the joint. Okay, so let's see. Somebody, when I asked the question, said, well, every node will be connected to every other node. They were right. Every node here is connected to every other node. And then to which I pointed out, well, you haven't told me anything about the edge directions. And now we can see that the way I drew it here, we have certain edge directions. Okay, now if you really understand what we're talking about, you can answer the following question. No, you can't. I'm sorry. You can answer the following question. Are there other legitimate graphical models that I could write down that represent exactly this same conditional independence assumption-free joint distribution? Yes. So what would be one of them? Thank you, right. So just pick a different variable than x1 to begin with. In fact, I could just invert all these. I could do it this way. This would have been a smarter way to ask the question. That would work, right? I can permute the names I put on the nodes because it's just the same as saying I'm going to apply the chain rule in a different order. I can't just arbitrarily move around those arrow edges directions one at a time. I think that doesn't work. But that would be a good thing for shower time. Think about that one. Okay, but now you got it, right? If you get this, you're really in the swing. Because now you can go back and forth between the graph structure and the factorization of the joint distribution. And that's what it's all about. And that's where the conditional independence assumptions come in. Because the terms in that factorization, the more conditional independence assumptions we make, the fewer things are on the conditioned on part of those terms. All right, let's go back a few slides because there were some other interesting things here along the way. So what we just did was we just illustrated an algorithm for writing down a graphical model for a joint distribution. Here's that algorithm that we went through. Basically, we choose an ordering on the variables that we're interested in the joint distribution of. And then we add one of those variables to the network. We ask ourselves, what does that depend on? And then we just add in their parents, and then we pick the next one. And that's basically what we were doing when we applied that chain rule. And if we do it just with the chain rule, then we just get the chain rule of factorization. But if we want to bring in conditional independence assumptions, then instead of expanding out each term in the chain rule the way it would, we can throw away some of those dependencies. Okay. All right, now here's a simple thing. Suppose that I want to write a Bayes net now, and I go to my doctor, and I say, tell me something about medicine, and she says, well, nasal problems can be caused either by the bird flu or allergies. And then she says, and furthermore, if you have nasal problems, that can cause sneezes and headaches. And I say, thank you, I now have 5 random variables you've told me about. What's the Bayes net? So what would you write down? Let me put nasal problems here in the middle. So I say bird flu can cause, let's call this F for bird flu. Well, that can cause, so it certainly influences nasal problems. Okay, and I'm going to make bird flu a Boolean variable. I'm going to make all these Boolean variables. So if I'm going to do this, the first thing I have to do when I'm trying to do modeling is say, what are the random variables involved? And what type of variable are they? The Boolean, real valued, vector valued? Okay, let's keep it simple. And suppose we say here, we'll use Boolean values for random variables F, A, N, H, and S. And now, if my doctor tells me that nasal problems depend on bird flu, I'll do this. But they also can be caused by allergies. I'll do this. Now, I could put an edge between A and F, and then I would be saying there are no conditional independence among this triplet of variables, because that's exactly what the chain rule would have given me as the graph. But since she didn't say anything about bird flu causing allergies or allergies causing bird flu, and I'm enough of a doctor to know that there's no reason to think allergies cause bird flu, so I'm not going to put an edge there. On the other hand, if they cause sneezes and headaches, then I might do this. I wanted to go through this kind of a simple example just to kind of get the intuition that these arrows really are our way of writing down kind of the complement of independence assumptions. The arrows really represent dependencies that we think occur. And then the arrows we leave out, those are compared to the joint distribution. It's those arrows that imply, the missing ones that imply the independence assumptions. Okay, so given what we know about Bayes nets, namely that every node is conditionally independent of its non-descendants given its immediate parents, tell me a conditional independence assumption that follows from this. Can you give me any about N? Are there any conditional independence assumptions that N is conditionally independent of something given something?
H is conditionally independent of F.
Yeah, but you're not answering my question. I'm asking, is there one for N? No, there isn't. I don't see one for the rule that we've said. Node is independent of its non-descendants given its immediate parents. N has no non-descendants given its immediate parents. So I don't see any there. But for H, we could get one, right? What's H conditionally independent of given its immediate parent, N? Right. It's independent of all those things, right? So H is conditionally independent of S given N. H is conditionally independent of A given N. H is conditionally independent of F given N. Again, just by applying our simple rule. Conditionally independent of your non-descendants given your immediate parents. Okay. All right, very simple. Another simple question to test your understanding. What's the graphical model, the BayesNet, the directed graph, for naive Bayes? Suppose I'm training a naive Bayes classifier to predict P of y given x1 up to x4. So I have 5 random variables here. And of course, with naive Bayes, I assume for every x sub I and x sub j, they're conditionally independent given y. Or put another way, I am assuming that P of y and x1 and x2 up to x4 can be written how? What's the factorization implicit? Right. It's Py right? That's our assumed factorization of the joint distribution. So what does that mean the BayesNet would be? So it means y has no parents, x1 has one parent, x2 has one parent, etc. That's the graphical model for naive Bayes. Right? By the rules of the game, we could, we could derive it the way we just did. We just say, well, we know what the factorization of the joint implied by naive Bayes is. Then we can just convert it to that graph. Or put another way, what are the conditional independence assumptions implicit in this graph by our rule about, let's say, x1? What is x1 conditionally independent of its non-descendants given its immediate parents? Beautiful, right? x1 is conditionally independent of x2 given y. x2 is a non-descendant of x1. It's conditionally independent of that given its immediate parent, y. And similarly, for any x sub j not equal to x1. So all those conditional independence assumptions between all pairs of xi's and xj's fall out of this graph. So it is, this graphical model makes exactly the commitments of naive Bayes. They're equivalent. One of the questions I was going to ask you, guess we won't use this one for the midterm, was what if you started with naive Bayes and you just wanted to say, I hate to assume that x3 and x4 are conditionally independent, but I'm willing to go with everything else. Just add one arrow to this graph, right? Oops, let me add in x3. So now how do I modify this to say, I believe all those conditional independencies, except I don't believe x3 and x4 are conditionally independent given y. Then what do I do? Yeah. Which direction do I make that arrow go? Doesn't matter. Why doesn't it matter? It doesn't matter. Why? Because basically what I'm saying is I need a term like this. I'm no longer willing to say that that can be decomposed into the product of x3 given y times x4 given y. That's no longer what I'm willing to consider. And so I need that term in there. And by the chain rule, I can write that either P of x3 given y and x4 times of x4 given y. That's one way the chain rule will allow me to write it. Another way the chain rule would allow me to write it is just to switch the role of x3 and x4. Right? They're equivalent. Chain rule doesn't care which order I expand things in. If I expand it one way, I get the edge going one direction. If I expand it the other way, it corresponds to the factorization with the edge going the other way. So it just doesn't matter. Cool. Okay. Here's another easy question. So far we've been talking about Boolean random variables. What if I have a mixture of, let's say, Boolean and real valued random variables? Like, let's say battery power there is a real value. It's what's the percentage of battery life left? Whereas fuel pump is 1 or 0. Is the fuel pump working? So we have some Boolean variables and we have some real valued variables. What does that do to us? Right. So it actually, the interesting thing is it doesn't change the factorization at all. The rules of the game just tell us how to factor the joint distribution into these product of conditional distributions. We haven't changed the rules of the game. We get the same factorization. So the only thing that changes is if we have to now represent the probability of x sub I conditioned on x sub j. Well, if xi is a Boolean variable, then we'll use a Bernoulli distribution to model that. We'll have one parameter to estimate for each configuration of the parents. We'll have to have a theta parameter that estimates the probability that the Boolean variable will take on the value 1 and a different one for value 0. Oh, they sum to 1, so we just need that one parameter, right? Standard Bernoulli distribution on a Boolean valued variable. Now, what if it's a real valued variable, like the battery life? Well, then, just like we chose a Bernoulli distribution for the discrete valued variable, for the Boolean variable, if it's a real valued, we need to choose some other kind of way of representing the conditional distribution of battery power, how it depends on its immediate parents. It only has 2, battery state and charge. But we need some way of representing the probability of battery state, or say battery power, given battery state and charge. And if we're assuming this is real valued, then we just need some other, we can't use just a Bernoulli distribution to represent a distribution on a real valued variable. We need something else. And there are a lot of distributions to choose from. One we've already talked about is Gaussian distribution. We could make this a Gaussian distribution, for example. We could say that this is just a normal distribution with some mu which is conditioned on the parents and some sigma which might also be conditioned on the parents. Right? So there's really no problem with mixing and matching Boolean and discrete valued variables, Boolean and real valued variables. Right? We get the factorization is, and this is one thing that makes the BaseNet such a useful abstraction. The graph doesn't tell us how we must represent those conditional distributions. They might be Bernoulli, they might be Laplace, they might be Gaussian, they might be something else. The only thing it tells us is up one level. It says you may factor the joint distribution over all these variables into the product of these terms. Now it's up to you to choose how you want to represent each one of those terms. So you see the graphical model, which has these two parts, the graph and then the representation of each of those conditional distributions. Well, the graph part is really non-committal. Doesn't care. The rules of the graph don't care whether they're Boolean or continuous variables. The only thing that matters is that second part where you have to write down the conditional distribution. And there, of course, you have to make some commitment about whether you're going to say this variable follows a normal distribution or something else. Now you could go back and you could ask, oh, how would I make a naive Bayes classifier that uses some combination of Boolean variables and real valued variables? It's just a special case of what we just talked about. So you could easily do that for naive Bayes now, too. Okay. Here's another interesting class of Bayes nets. We'll talk more, we'll do a whole chunk of time on this later on in the semester. But this is a Bayes net called a hidden Markov model that is very useful for characterizing time series or gene sequences or sequential data of a variety of types. And essentially think of this as, let's see, some people use this for example, language modeling. Some of the first approaches that used machine learning for speech recognition were based on hidden Markov models. And essentially, let's explain in terms of an example from speech recognition. We assume there's some sequence over time of observations O sub t and O sub t plus 1 and O sub t plus 2 and so forth at different times. In speech, that might be different phonemes that our microphone is picking up, different frequency power and different frequency bands at one time and at another time and so forth. Then we assume there's some hidden, that's why it's called a hidden Markov model, some unobserved by us, in the case of speech recognition, word sequence that's being said. We'll call those the S, the states, the hidden states of the system. The speaker has in mind a sequence of words. They're saying, the dog ate my, and we're picking up the sequence of phonemes. And so we want to estimate, we want a probabilistic model that lets us estimate the probability of that probability distribution on those unobserved, not directly observed word sequence given the observed sequence of phonemes. And hidden Markov model corresponds to a very simple Bayes net structure shown here, which makes obviously a bunch of conditional independence assumptions, but they're all of the form that the future is conditionally independent of the past given the present. Right? So, for example, if we ask, what about ST here? Or what about actually, let me ask it a different way. What about OT? So OT, of course, by our rule, is conditionally independent of all its non-descendants given its immediate parents. Wow. Everything is a non-descendant, and it has only one immediate parent. So this thing is saying the microphone signal that we observe, OT, depends only on the current state of the system, the current word being spoken, independent of the sequence of words that came before or the words that are coming in the future. What about ST? So ST is conditionally independent of what? So ST is conditionally independent of something given its immediate parent, which is ST minus 1, right? what do I fill in the blank here according to our rules? Yeah, so its non-descendants include st minus 1, st minus 2, also includes, did I make a mistake? Did I? O sub t minus 1 and O sub t minus 2. Yeah, I don't think I made a mistake. So those are all non-descendants.
Yeah, your first one's except t minus 1.
Oh, thank you. I did make a mistake. I had no idea how valuable this new technology eraser was going to be. Okay, thank you. So I did make a mistake. I couldn't include its immediate parent because that's what we're conditioning on. But it's conditionally independent of everything in the past, given its immediate past. It's then independent of everything beyond the immediate past, including all the observed things. Now, are there anything else? No, I got the whole thing, right? Everything else is a descendant. It's either an immediate child or a grandchild or a great-grandchild. So all these other things are descendants. So our rule does not imply necessarily that those are conditionally independent. And so what's the factorization here of the joint distribution over these variables? Let's start with the one that has no parents. That's always the easy place to start. So I'll write that down. So the joint distribution over, so if you tell me I observe these green microphone signals and I hypothesize a sequence of states with this particular sequence of values, then I can figure out the joint distribution, the probability of that joint assignment to all 10 of these random variables by factoring it just according to my rules, right? It's the probability of this superparent times, oh, let's take this guy next because he just has one parent. Times, well, let's take this guy. Given st minus 2 times, et cetera, right? And then what's the next term if I want to write down this one? It's the probability of O of t minus 1 conditioned on just his immediate parent. So this breaks down into a beautiful set of very simple two-variable distributions, right? So that's a hidden Markov model. We'll have a lot more to say about it. In fact, a brain teaser to think about is you lie awake at night is how would I train such a thing given that I only get to observe the green colored variables and I don't even get to see the values of the white variables because they're not observed directly. But I believe that they exist and that's why they're in my probabilistic model. How would I train such a thing if I can't observe all the variables? Good question to think about. We'll talk about it in a week. But for now, let's ask the much simpler question. Suppose in general you have a Bayes net and you want to train it. Now what does it mean to train it? So it can mean a number of different things. In fact, roughly speaking, there are 4 different learning problems that people consider for Bayes net. We might assume that the graph is given. Let's assume the random variables are always given. So here's a collection of random variables. So we could assume the easiest one of the 4 problems. We assume the graph is given, that commits us to a collection of conditional independence assumptions. The graph is given, and all the variables are observable. So every training example is really the values of every one of those variables. So every day I go out and I look at my car, I measure all those variables, I write down one training example, the next day I get another example, and so forth. So if I want to train the Bayes net with fully observed variables, and I know the graph structure ahead of time, you should know how to train that Bayes net right now. So what does it mean to train that Bayes net? It means, well, we already know the graph structure. The only other thing remaining is those conditional probability distributions. How would we learn those? You already know the answer. It's the same as naive Bayes. In fact, training naive Bayes is just a special case of a graphical model of Bayes net, where you have fully observed, you know all the x sub i's and all the y's. You get your maximum likelihood estimates, or if you're choosy, maybe your map estimates because you brought in some priors on those parameters to begin with. And all those parameters you estimated for naive Bayes by just counting up how many of the times x sub I was true, given y was true, and how many times it was false, given that y was true. It's exactly the form of the conditional probability. That's the only thing we have to learn here. For every node here, we have to learn its conditional probability table conditioned on its immediate parents. So it's just like training a naive Bayes classifier with fully observed variable values on every training example. And in fact, if we wanted, and if you wanted, you could go back to our derivation of the maximum likelihood estimates, and you could say, well, let's see, the parameters in the Bayes net here are just all the parameters in all of the conditional probability tables. Let me write down an expression for the data likelihood, the likelihood of my training data, given those parameters. Let me derive what it would mean to get the argmax over theta of the training data likelihood. And if you work that all out, you'd get exactly the same MLE estimates and the same map estimates that we got for naive Bayes. And that's what we're thinking through and really trying to do, just so you really convince yourself that you understand this. Okay, so that's it for today. I want to just ask you to do one thing. On slide 1 here, it says required reading, Bishop's book, chapter 8, up through section 8.2. Really do that. Do it before next lecture, and you'll be happy you did. It's a well-written section, and if you happen to not own a copy of the book, even though it's officially the required text for the course, that happens to be that chapter 8 is a freely downloadable chapter graciously made available by Chris Bishop. So we'll try to put a pointer to that downloadable chapter, but you can find it for free on the web too in case you happen to not have it. But the reading is really useful in this case. Okay, see you Thursday.